Thank you for the introduction. Yeah, I mean, maybe we're not too famous, but we were at least in all the newspapers who were reporting about the Meltdown CPU vulnerability. However, so that was great. Quite a gift for a startup like us. Okay, I'm a co-founder of this company, Cyberus Technology, and I will not talk too much about the technology or, the company or the technology. It's like we are the our first use case for what I'm going to present. So I will present a bit about us and our main product as a user context kind of, and then we'll quickly go over to actual testing. So what is Cyberus? Cyberus is a German cybersecurity startup. We were founded just 1 year ago. And the founder team was ex-Intel and FireEye engineers. So we come from the CPU architecture side and security a bit. And we basically develop our own secure hypervisor based on microkernel technology. And that thing ought to support like everyone's laptop. We are kind of growing with that support. And that makes it also hard to test, which is why I'm here. Okay, so I'm talking about testing of bare metal or embedded system projects, which I regard as a kind of class of projects, where I hope that some people will identify to here. And what I mean when I talk about a bare metal or an embedded system project is software that runs bare metal, not just you double click on it and it runs on Windows or Linux or whatsoever. You are actually the abstraction for the hardware and you're not using any abstraction for the hardware in that sense. So if you want to test your stuff without mocking anything, you need to boot it on real hardware and see if it works. And in our case, we are developing a hypervisor, so it's not just booting an operating system and seeing if it works. We're booting it on many different hardware platforms. It ought not crash on those. And then we are also booting different guest operating systems. So when we boot the hypervisor, which then boots Windows as a guest operating system, or Linux, or whatsoever, that also must not crash. And this is what we need to test against. And what you find yourself in usually when you are in such a project, not talking about hypervisors, just hardware-dependent stuff. You usually, when you use Git, you create a branch, develop your feature or bug fix, and while you're doing that, of course, you're doing test-driven development, so you can execute your unit tests all the time. And the thing which comes here when you do bare metal or embedded projects, you need to do kind of integration test runs. So ideally, every developer has on his desk a little test machine which he can boot and see if the stuff really works, and not only in the unit test or on VMs, stuff like that. And yeah, so at some point you're done. Feature works, bug fix works, whatsoever. And you start a merge request. And what you do then is the whole team rushes over it, reviews the code, gives suggestions, and you have some iterations until everyone is fine with it. And eventually you would merge it. While reiterating over the code, of course, you're testing it on your little machine again. So maybe you would need a box here. Yeah, whatever. So you get the picture. And eventually the code is merged because the feature is done. Yeah. And then you have some kind of QA. Because let's say we are supporting 30 different platforms, but the developers just are testing one of this all the time. Maybe every developer has a different platform on his desk, but if you support like 50 platforms, you most probably don't have 50 developers who test all those platforms all the time on their desks. So you have situations where the QA team or some manager who wants to present the stuff or salesman or whatever boots your product on another hardware platform, which is not regularly tested by the developers all the time. Or it's a platform which is usually used, but not in a use case you have a test for. So that are the cases where the product can brick, and yeah, that's bad. Then, of course, the QA or manager or whatever user will report that bug. So you know, okay, well, maybe that's even a regression because it might have worked one day already, but then it doesn't any longer. And then panic. Programmers are running in circles, trying to use git blame and git bisect in order to find out who introduced the bug when and who's going to fix it now. And that's basically, if that is shortly before a deadline or an important customer has this problem, you rush to get the problem out. So This is kind of a problem when you have kind of this, getting regressions that just strike you kind of suddenly because you're not always executing all the test code and customer scenarios on all the hardware all the time. You will regularly have this. So some years ago, I was newly hired into a project where we wrote a hypervisor from scratch. And I was not too experienced, and we were a few guys who were not too experienced, mixed with experienced ones. And of course, we from time to time fucked up the product because, yeah, it ran on the machine I have on my desk. 2 weeks later, we find out some manager wanted to show it somewhere, and on his laptop it crashed. And the solution was obviously not stacking 20 computers on everyone's desk who develops this, right? So we had kind of, this situation occurred regularly in some sense, but we didn't see any real solution to that. And this is not only about developers who panic when they think of overhours. Of course, this is a problem also to management, but you have more problems following this one. One thing is, when you have kind of separate development and QA, it's very tempting maybe for the management to say, well, let's buy some smart developers and use their time efficiently to do the hard feature and bug fix development, and move QA to another country or continent where the guys just concentrate on executing all the tests on all machines. So we have kind of a feedback loop, and it will not take months until we see that we have a regression for months now, but maybe weeks or days. And the problem is then that if QA works quick, they go to the developer and say, well, we found this bug, you introduced it like last week. He is already working on the next feature, and then realizes that the other feature wasn't really done yet because it doesn't run on any other platform than his one, for example. So this is kind of a phase shift in this feedback loop. The other thing is if that's what I just said. Okay, sorry. The other thing is developers might introduce changes to the product which break the actual tests, but they don't notice because they didn't write those tests and they don't execute them, and QA sits there and, oh, well, is this a product defect now, or is the test obsolete, and how do I fix that? They didn't inform me. So this is very frustrating, and I guess that QA people feel very much like second-class developers in such situations. And then they go to developers and bother them like, well, look at this test, please. And developers say, I have no time for your tests, please fix them. And yeah, this is kind of I have experienced this too. It's not cool. Yeah, and you have this overhours rate, of course, which is, for the manager it's bad because he cannot sleep well when he's not knowing if you're always regression free. QA has bad times sometimes. Usually this stacks up before release weeks, kind of. And then everyone is like, okay, oh my god, we have release tomorrow, but now we found the bugs. What about finding them weeks earlier? So, however, these are different symptoms of the actual problem that you merge code without really knowing that all the scenarios work on all the supported platforms. And you do this because you don't see a real solution to do that, because you cannot really execute all the tests on all the platforms all the time. And so we found that this is really painful, and we improved the situation by developing an automatic test platform which actually does this. Execute all the tests on all the machines in every pull request. And so what we came up with is this. You open up a pull request and you get this matrix. Is John's code regression free? Obviously it's not if you have a single red cross here. So what this table is actually showing, you have, sorry, I didn't realize that the font is very tiny. So the columns are, this is one machine, this is another machine. You have like 15 different machines here. Let's say these are the 15 different supported hardware platforms. And you have different tests here. So ignore the first ones too. These are expected fails. So if those don't fail, the test infrastructure is obviously wrong. But here you're booting Linux with different parameters in a command line, and then it must work, however, with whatever configuration we boot it, because then the hypervisor works fine. And there are tests which just consist of toy operating system binaries, which test individual aspects of the CPU, which is then the vCPU in the hypervisor context, of course. And you want all tests to always pass. And then you say, well, now we can merge the code. And so this way, we were able to reject all pull requests, or all pull requests that do not succeed on all machines with all the tests. Because the situation is, maybe John has a Carlo machine and his test ran just fine, and he can't know that he introduced some regression. And this way we know it because the automatic test framework does this for him. And so what we came up with is the whole table. It executes in like 30 minutes. So you open the pull request. Yes? Oh, that is a very old screenshot. Please just ignore the expected fail lines, right? But you're right. If you're expecting the fail, it should be green. That's true, right? Yeah, however, so actually you want this feedback loop where you can reject code that introduces regressions before you merge it, instead of the QA team, or even worse, some important manager or client finding out. And this gives you such a feedback loop. So it's only differing to the first one, where we have full integration test runs all the time. And when we improve the code, we have full integration test runs again. So we are always sure before merging the code. And this way we are completely regression free. Because if something that worked yesterday stops working with the John's pull request, we don't merge it. And then he has to fix it, and it's fine again. And so what makes it so complicated to actually have this? In our case, we have the developer machine on the left, and the test hardware on his desk, for example. And so our hypervisor is an Intel platform hypervisor. So this is a machine which might look just like the developer machine. But it could be an embedded system too, of course. And in our case, we just reboot the machine, feed it with binaries that it ought to boot now, like the hypervisor, and then its chain loads Windows from the hard disk or Linux or whatsoever. And after boot, the tests execute, and we get results back via some kind of serial line. So there's a legacy serial cable, or serial over LAN, or some USB debug cable. It doesn't really matter. We just need some kind of standardized channel for test output back. And that might look just like unit test output, like pass, 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 fail, and then all the tests failed. The thing here is, if you have 100 tests which test different aspects of the system, like we boot and try to program some interrupts, and if they are fine, then the test has passed, and then we boot the next one which tests something else. And we do that on 30 platforms. We have 3,000 boot cycles that need to be automated somehow. And of course, no one's doing that by hand. It gets even worse when we look at our actual project at Cyberus. So what we have here is we first boot a microkernel on the system. This is some 10,000 lines C++ microkernel. It's the only part with our hypervisor that runs in most privileged hardware execution mode. It's host mode ring 0 in Intel lingo. And of course, we want to test that thing. So we would boot the microkernel, boot some, let it load some test case, and it tries to manipulate the kernel and see if everything works right. So we have multiple of these. The next thing is, the root task is kind of, when you couple it with the microkernel, it's the actual operating system. It manages all the memory and so on. So these two work together. This one implements mechanisms. This one has the policies, and together they are kind of a secure operating system core. And the root task provides services to the next applications which run in the same user space. And so we are also launching tests which test the root task that plays together with a microkernel. So there's a different kind of binary, and you have different ways to load them. Then the next thing is, when we are testing the actual hypervisor, we want to boot some kind of kernel. So that is a toy operating system binary which does some simple things, or it's a full-blown Linux or Windows. And we want to boot that things with and without the hypervisor, because if they execute just the same way, then the hypervisor behaves like the real hardware on all the platforms. And then another testing surface is applications running in the guest user land. So maybe you want to play computer games without crashing on the hypervisor, without any visible overhead. We want to run maybe browser JavaScript benchmarks. If these go much slower with the hypervisor, then the hypervisor is crap, and we need to tune that out. So these are those four different kinds of testing surfaces. And they further multiply the number of reboots necessary, because we have n tests times all the different hardware times all the different guest operating systems. So that might be Windows 7, 8, 10, Linux A, Linux B, Linux C, whatever. So we need to do a lot of reboots with the same tests on that changing conditions. So, and we want a new kind of the developer should not be bothered with how to boot this machine or how to boot that machine. He should just develop the actual product, the tests bundled with it, and some kind of recipe how to test this if you have the infrastructure for that. So our new separation, not between development and QA, goes between development and the administration of test infrastructure. The developers do test-driven development like before, but they also specify for all the bootable tests how to boot them and what kind of combination with what, and which also define the execution environment. So boot this test in the hypervisor, but after you booted Windows or Linux this time. And so you have kind of the output of this. It might just drop out of your build CI. It contains binaries and test recipes, and that's it. And if you have the right infrastructure to execute that, you can just do that. At the other side, the administrators, they maintain the test infrastructure and set up operating system templates like the Windows which you boot from somewhere. And together you can throw it at the automatic test execution engine and will produce that nice table where hopefully all the boxes are green check marks. Okay, so what about QA then? We just kind of killed a lot of QA jobs, or at least it looks like that. We actually didn't. We just say that QA people should sit in the same team as developers, sit next to them and write tests still, so they are trying to brick the product before the client does, or a manager. But they can communicate with the developers more tightly, because the developers are, if they provide pull requests with the tests in the same repository, they are forced to not brick the tests by changing the product too much. So if I am a developer and implement something that makes some test fail, I can go to the test, or I have to go to the test person and say, well, we need to work together to keep this test working, because otherwise it looks like I introduced a regression and I can't do that. So you are killing this kind of phase shift in that feedback loop, and no way that 2 weeks later someone will tell you that there's a regression, because you have to fix it now. And that's again what I just talked about. The thing is, what we do here is, when we hire new people just from university who are not really experienced yet, we first declare them as test writers, and this way they really learn the product, and at some point they're experienced enough and can start implementing features too. So we have kind of an evolving career from QA guys to developers, and at no point in time they were kind of second-class developers or second-class QA people. Okay, so what do we have there? When I talk about this thing which produces those giant test tables, the architecture of this, what we have in deployment right now is we have this test service, which is basically a database with a web UI. So you can see what kind of test runs you have, on which checkout of the code, and how much tests you have and how many machines. And you have the machines, of course. So those 15 different platforms on the earlier screenshot, that might be 15 different worker machines controlled by a controller, And I painted 2 here because this can be distributed. So you have one controller with one set of machines, another controller with another set of machines, maybe in different contexts, continents, I mean. As long as they report to the same database, you can split it up. And yeah, so when you open a pull request, your GitHub or GitLab CI chain will trigger the test service. And as a part of the pull request CI, you get this test run created, which then runs. So the controllers are regularly polling for work. Then they find some work, ask for the binaries in order to perform the work, and then they will kind of boot all the worker machines. What's really nice is when you open the pull request, you can see in our server room how multiple machines are starting to boot now, and there's a lot of noise suddenly going, which feels really productive without doing anything. Okay, then we boot those machines via network because this is the easiest way to give them different binaries at every boot. Then we'll collect the logs and write back the results at the test service. And yeah, this is how the whole architecture works. So you have some kind of CI which gives you artifacts for downloading, and the GitLab thing, it's aimed to seamlessly integrate into any kind of build environment which you might have. Yeah. And then talking about the performance. So let's say you have really a lot of tests, it might be hundreds, and even more machines which you support. That ought to be fast, because otherwise, when you realize it's unrealistic to run all the tests on all the machines on every pull request, you will at one point stop doing that and suffer from the old problem. So that needs to be fast. And what's really trivial to see is that, of course, when you have different machines standing next to each other, they will, of course, execute in parallel. But the other thing is you can buy more hardware of every specimen, and then you will have the columns also executing in parallel. So if you double up the team to more developers who run more tests, you can double up your hardware too and have the same amount of tests per minute. So we are kind of future ready in that sense. When you're having the growing team and growing list of hardware support and growing list of operating systems you support, you buy a few more machines and the problem is solved. So this was one example deployment. We had this server rack. There were a lot of exotic mainboards which we stacked up. So we tried to get all the different Intel chipsets from the last 10 years we could get. So some we bought on eBay, some on Amazon or whatever. And we had all the variety. Then we had some customer laptops, consumer laptops, I mean, Intel NUCs. Then here are 3 more machines. They were actual developer test machines. And they were very heterogeneous, completely commodity products, not built for debugging or whatsoever. This is just how you can get them at the supermarket. And so we plugged them all in into the server rack, and bam, there we have our test rack. And when the hypervisor survives all the tests on these machines, you're pretty sure that, yeah, it's fine. Then the other thing is, actually, I started developing the first version of this at our former employer in my home office. So I had these IKEA tables for €5 per piece. Some screws and nails and so on. Here I stacked up a few machines. There's a Lenovo laptop, a gaming PC, and there I had some different chipsets to play with. They were all connected via network. Actually, this machine has no remote power switching. So what to do? Those machines from the supermarket are not built for testing. So we have a little Raspberry Pi here. It actually has an optocoupler, and it pulls the power button for 1 second for switching it on and 5 seconds for switching it off. And that's how you can transform any machine into a nice test resource, right? And that one works with the real serial cable, the legacy one, and just plugged in a PCI card with serial capabilities, and that's it. These machines are all fine. They have remote power switching. It's IPMI boards. This has the Intel AMT Trojan Horse mainboard feature, which nearly everyone has. So you can get remote power switching and serial here for free too. The Lenovo 2, and yeah, that's it. So we actually had this one and that rack reporting to the same database. And from the web UI, you didn't see the difference. You didn't see that this is some kind of ghetto setup and that one is a real setup. It's just abstracted away from you. So in order to have this running, and this is where commodity systems with Intel chipsets and embedded systems are not too different, is you need to remote power cycle them, of course. You need to do some kind of network boot, because this is the easiest way to get different binaries onto it on every boot, and serial output. So for remote power cycling, we have this nice Raspberry Pi thing. So I just soldered some things together. This is a Raspberry Pi shield. We can map the power buttons to GPIO pins, have a little Python script that does power switching via HTTP requests. Really simple. Or you have the full-blown Intel AMT or IPMI interfaces. Network boot is possible via iPXE. That is really nice. Grub would be possible too. It's all basically multi-boot on Intel. And the serial output, we had different partly funny ideas. Caps lock is really interesting because, so what you can see here, I don't know if it's too dark, the contrast. So this is a keyboard, and if you have a computer which has no serial interface visible or usable for you, you can use the caps lock light and morse characters out of it. So we actually did that, right? But I have to say that was not my idea. That was the idea of our hero who also discovered Meltdown, right? Yeah, so that's this kind of genius we have in the founder team. And yeah, so using those tools, we are able to abstract any kind of commodity machine to a test resource that is remotely rebootable, which can be fed with binaries and then will somehow produce a serial output that is a witness of a failing or a passing test. And I think that is something which does not only apply to Intel boards, it's any system can be regarded like this. Then when you look at the individual test output, you can click through the whole matrix and you look at one failing test and you want to see details. You don't have to have that machine on your desk, you can just see the recorded log output. In that case, we have a kind of a passing test, so you can see a lot of debug output that is not relevant to the test directly, but then you see so test version 1, begin 3, that means protocol version, and we have 3 tests following now. So we want to see 3 success messages and an end message, then we can stop listening and we know that the test passed. And all our tests look like this, basically. We invented this little protocol, although there's Google Test and the Test Anything protocol, because we needed some more things. For example, when you have a test which needs to boot Windows first, and then some test, then takes quite a long time, so you need to wait for the next output line. But in contrast, when you have tests which are really fast, you want to stop listening after 5 seconds if you know that if it's taking more than 3, then the machine obviously crashed because the test is usually faster. This way we can accelerate the test execution because we know which tests are fast and we can be less tolerant against lags, kind of, and which tests really need us waiting. So we have kind of programmable timeouts and so on in that protocol. And that turned out to be really useful. Yeah, so the first version of what I just showed you was at our former employer. It was just a bunch of Python scripts. And the problem is that the complexity got down on us again because this was something no manager allowed us to do in our main time, although it was very valuable. So we did it in our free time. And that was just some hackery and scriptery. It just worked, and we hoped that it runs for multiple weeks without touching it. And we're happy already. But yeah, so summer 2016, the whole project was cancelled. We were all fired. And so looking at the last year, that was the best thing that could happen to us. Because we started this new company with the same team, basically. And we thought, yeah, we need such a test solution again. But this time we will develop it with the same standards as our actual product. So we do kind of real code reviews, unit tests, integration tests, static analysis, and so on. We implemented this not in Python, but in a type-safe compiled language. So if our SQL joins don't make sense because we changed the types too much, it doesn't compile any longer. So we have also the solution which keeps our product regression-free is also pretty much regression-free at this point. And while the Python script solution was very hard-coded to our needs, we are now kind of making product quality and keeping the product generic and configurable, first-class design goals. So it might be useful to other people too, because we thought, well, if we invest so much effort, let's from the start design it in a way where you could also sell it as a product if it comes to this. Then we have this scaling very well, so we can have a lot of controllers in home offices of people, or if it crashed on your mother's computer, you could kind of temporarily create a controller over Christmas at home at your parents and hook it into a test rack and then see if it's worth buying such a machine for the company too, and stuff like that. It's really easy to set up actually. So in February we had our 1-year anniversary party, and we had our employees kind of setting up demo machines, and we had also a demo setup of this, and it just took 2 hours to make everything work. It's a completely isolated environment with a few test machines. So it's not even a day which is wasted if you configure this, it's just hours. And it's completely integrated into the CI. So we don't really need to do any manual steps in order to have the whole testing hell suddenly working as soon as you open the pull request, which is really nice. Because, yeah, no manual steps involved, no QA team involved, nothing. It just tests everything all the time on all the platforms with all the guest operating systems, and yeah. Okay, so this is really nice. We have a better life since then because we have regression-free development of a hypervisor with a very small team of less than 6 persons. And when there's a customer who says, well, yeah, your hypervisor looks great, but does it run on platform X? Then we can just buy a platform X, hook it into a test rack, and 2 weeks later it's passing all the tests there too. And then we can tell them, yeah, how about buying it now? Because we did everything and we did quick. The future of this thing is we have, of course, growing testing needs now, because when it's so easy, you quickly start thinking about the next step. And those steps are, for example, when you're used now to have 100 machines testing your stuff all the time, what would you think of now? So you can also say, well, talking about performance of things, let's build our kernel this way and see if it actually improves the performance on all 100 machines which we support. Or is it running very, very fast on my development machine, but slow on all the others? And we can try different compiler flags, which are pretty much architecture dependent and so on. And this is really nice because you can kind of do mass grab calls and enumerate interesting information about performance or mainboard data structure geometry over all the machines you support. And quirks is interesting. So I've been working with ACPI a lot. I didn't really like it because there's so many pages of ACPI standard. Then you learned it and think, yeah, so I'm smart enough to implement this now. And then half of the machines push you back because they don't work this way, because they have all their quirks and different creative interpretations of the standard. And so with such a system, it's really easy to make your hypervisor, for example, support suspend and resume of the guest system. One moment. Starting suspend and resume on real hardware without crashing, because you can just try it on all the machines now. And then you see where isn't it working, get such a machine on your desk, and a few days later it works.
One solution we use in our company sometimes is to try to configure that thing on power on and put it out on a power relay, which has to be a digital console, and then you're there. Do you use that or consider that?
Yeah, so at our former employer, we're actually using programmable power sockets, which is nice, but we had cheap ones there and they weren't too reliable. And when we just started our own company, I was doing a lot of stuff in my home office, and I was like, well, yeah, I have this Raspberry Pi here. I'm not going to spend 100 euros into something when I can buy this in 2 hours now, right? So we had different possibilities there, and you can use them all, of course. So there's no real limitations. Maybe if you have some professional admin, he would say, well, go away with your Raspberry Pi hackery stuff. I just buy real stuff and yeah, so what will the insurance say when this Raspberry Pi starts to burn? Or I don't know. However, you're free to use whatever tool fits. Okay, so when you then have 100 machines, or 200 whatsoever, which produce a lot of testing output over the months and years, you can see how your product has performance regressions over time. So is it slower over the months? We didn't notice this from pull request to pull request, but now we can see some machine is like 50% slower than in January. This is what you can really measure now, and you can see which pull request affected this. The other thing is, oh, wait, performance numbers look like this. You can, for example, boot Linux with different configurations and see how much slower compared to another test run in the past it is on which machine. So, for example, we have a change which is doing just fine on those machines, for example, because we have only 4-person overhead. But here it's bad because you have 15-person overhead. So you can really nicely tune that away. And you can, of course, say, well, we have a lot of tests executing right now. Maybe we want to schedule the tests in a way where we execute those ones first, which very often fail, because then you can just avoid executing all the rest, because we already know that John has to fix some aspects of his pull request. And the other thing is, you can easily evaluate hardware for your product or your product for some hardware, because you can just plug the hardware in and there you have your results. You have no one trying if the product works on some new board, because you can just throw all the tests on it. Okay, then the next scenario which is coming is kind of orchestration of real hardware deployments and virtual machines. So in our case, our hypervisor, we will sell it as kind of a super debugger solution too, in the sense that the client would boot the hypervisor on some machine, run malware on it, and instruct the hypervisor from another machine to please look at this, interrupt here, interrupt there, please pump out some memory values, and so on. So kind of a debugger which works from the hypervisor layer without guest operating system support. And in order to test that, you would need to run the hypervisor on real hardware with some real operating system, and then launch some other machine with Linux, Windows, or Mac OS, running the client which communicates to the hypervisor. So you would kind of spawn a virtual network containing the machines you need, and this way you would have test scenarios where you're not only defining how to boot a test, but in what network to boot it in, kind of, which machines can see it, over which ports, who can see what, and what to execute on those virtual machines. So we're using VirtualBox currently, and already have such scenarios working. We're just productizing it so it fits into the whole product. And that's still with those decentralized controllers. Another thing is what we realized, well, wait, if we kind of stack up machines all the time, at some point you have, let's say, 200 machines which are in some important aspect different from each other. And you kind of, this collection itself is very valuable to others too. So maybe you could rent it as kind of a testing as a service platform, where some customer says, yeah, well, we don't have that many machines, but we would like to see if our product works on this variety. So they could just point their CI chain to our cloud testing service, and it reports back the results, because the system is designed in a way where you can just consume the binaries and testing recipes, and that's all you need to execute it, right? And yeah, so this is just a kind of a business idea. Maybe we will get to this at some point. If you find it interesting, let's talk about it. Yeah, and okay, so this is my summary slide. What does an automatic real hardware test infrastructure give us? It enables us to do full end-to-end testing before code is merged, and not after code is merged, not when some manager tries to execute it on some special laptop which hasn't been tested for months, and boom, oh no, it doesn't work. Who does the overhours now? It provides freedom of this functional regression. It's not possible in our products with our processes to brick something which has been working yesterday. It just doesn't happen any longer. Since we were founded, it didn't happen. It's really easy to add more hardware to our support list, because it's so easy to run all the tests on more hardware. it brings a lot of power to our small team, because so as like 4 to 6 core developers writing a hypervisor that can kind of run on all the laptops here in this room, it's completely possible now with this test system. And the other thing is we have no gap between development and QA people. We have no second-class developers who just write tests. They are just sitting next to real developers and have to work with them. The developers have to work with the QA people, because they are the ones who have to provide working pull requests, and not the QA people who run after the developers, like, please help me fixing your the test for your product. And it's very easy to have this coverage thing, our tests running on all the platforms and all the operating systems and applications. So you can multiply this, what do we test, very easily. Okay. Thanks for your attention.